The ocean floor. Dark, crushing pressure. A place where humanity cannot survive unprotected.
Yet something is moving down here. Silent, autonomous, relentless. To survive here, you don't just build a machine. You engineer a miracle. Welcome to the birthplace of the next generation of deep-sea explorers. Miles of wiring, titanium armor, artificial intelligence sharper than a human pilot.
One loose seal, one hairline fracture, and millions of dollars implode in an instant.
Today, we reveal exactly how these silent giants are constructed, from raw metal to ocean rover.
This is the future of ocean exploration. This is the AUV build process.
An autonomous underwater vehicle, or AUV, is a torpedo-shaped robot designed to map the world's last frontier.
Unlike ROVs, there is no tether, no cable to the surface. Once it dives, it's on its own.
Building one requires a facility that is part shipyard, part NASA laboratory.
It starts here, in the CAD suite. Every millimeter is simulated before a single piece of metal is cut.
The shape must slice through water with zero resistance to conserve battery life.
But the real enemy is pressure. At 6,000 meters, the water pushes with the weight of an elephant on every square inch.
Standard steel would crumple. We need grade 5 titanium.
And to float, we don't use air tanks. We use syntactic foam, a composite made of billions of microscopic glass spheres.
Production begins with the pressure vessels. Massive CNC mills carve titanium into precise rings.
Tolerances are measured in microns. If the seal isn't perfect, water will find a way in.
These ribs will form the skeleton, holding the electronics dry while the ocean tries to crush them.
We are starting to 3D print titanium parts to reduce weight even further.
At the end of their life, the titanium and lithium are fully recyclable. Meanwhile, the syntactic foam blocks are shaped to form the vehicle's outer skin.
The foam is porous and fragile. It receives a protective armor of fiberglass and epoxy.
The foam blocks are fitted around the titanium skeleton. A perfect engineering puzzle. Inspectors check every seam. Any gap creates drag and unwanted acoustic noise.
Reliability is the currency of the deep. There is no AAA underwater.
Every step is documented. The paperwork stack is as heavy as the vehicle.
Dust is the enemy of optics. The camera bay is assembled in ISO Class 7 clean rooms.
But a hull is just a shell without power. These drones need to run for days underwater.
We use high-density lithium-ion packs, similar to electric cars, but customized for extreme safety. To prevent the batteries from being crushed, they are oil-filled and pressure-compensated.
Safety is paramount. Each cell is fused to prevent thermal runaway deep underwater. Quick-release latches allow engineers access to the battery bay in minutes. A flexible bladder allows the internal oil pressure to match the external sea pressure instantly.
Heavy-gauge copper connects the power plant to the propulsion drive.
The heart of the movement is a brushless DC motor. Efficient, quiet, and powerful.
There is no physical shaft penetrating the hull. We use magnetic couplings to spin the propeller through the solid metal wall. The propeller itself is carbon fiber,
designed to reduce cavitation and noise.
4 rear fins provide steering. Independent actuators adjust them hundreds of times a second. Before installation, the propulsion unit is run at max RPM to check for vibrations.
Underwater, GPS signals are dead. The AUV is flowing blind.
On that, the solution is the inertial navigation system, or INS. A laser ring gyro so sensitive it detects.
It must be mounted perfectly aligned with the vehicle's center line.
Assisting the INS is the Doppler velocity log, which pings the seafloor to track speed. The mission computer processes all this data. It's a ruggedized server squeezed into a tube. Electronics generate heat. In a sealed tube, that heat has nowhere to go. We use the hull itself as a heat sink.
Hundreds of cables connect the sensors to the brain. Cable management here is an art form. Now for the payload. This is why the robot exists: to see the unseen. The star of the show is the synthetic aperture sonar. It creates photorealistic maps using sound.
In the nose, a multi-beam echo sounder maps the topography ahead, allowing the AUV to hug the terrain. High-powered LED strobes and 4K cameras capture visual proof of shipwrecks or pipelines.
Every sensor needs a penetration through the hull. We use subcon connectors, gold-plated and watertight. The nose, the body, and the tail are finally brought together. 2 rubber O-rings are the only thing standing between the electronics and the crushing ocean. Titanium bolts are torqued to exact specifications. Even uneven pressure could warp the seal.
Before it touches water, we pull a vacuum inside the hull. If it holds the vacuum, it will hold the ocean out.
The vehicle must be neutrally buoyant. We add lead weights to balance it perfectly.
High-visibility yellow paint ensures the vehicle can be spotted in rough seas.
The paint is baked on for durability against salt spray.
The hardware is complete. Now, the software engineers breathe life into the machine.
Gigabytes of data are offloaded via high-speed optical links.
The mast contains iridium satellite antennas to talk to the ship from the surface.
It runs thousands of virtual missions in the simulator before it ever gets wet.
The AI is trained to react to obstacles, currents, and system failures without human help.
The moment of truth. The test tank.
It enters the water. South Asian male engineers watch for bubbles, the sign of a leak. It floats perfectly level. The ballasting calculations were correct. Fins cycle. Propeller spins. The beast wakes up.
We test the sonar pings in the controlled environment to calibrate the sensors.
But a shallow tank isn't enough. We put the entire vehicle into a hyperbaric chamber.
The chamber simulates the pressure of 6,000 meters. The hull compresses, but holds.
The propeller is dynamically balanced to ensure zero vibration.
If systems fail, a drop weight is released, making the sub light enough to float to the surface automatically.
At depth, there is no light. The LED strobes provide 50,000 lumens for the cameras. Electric propulsion means these explorers leave no pollution behind.
Passed. The vehicle is cleaned, polished, and prepped for its first real mission. It takes a team of 50 engineers to build just one of these machines. It's packed into a custom shipping container, ready to be flown anywhere in the world. We join the team at sea. The research vessel is rocking in the swell.
Final pre-dive checks. GPS lock, satellite comms, battery full.
Pilots train in simulators for months before controlling the real thing.
The A-frame crane lifts the 2-ton robot over the stern.
Release. It angles its nose down. The propeller engages. It says goodbye to the surface world. Hours later, it is miles deep, flying silently over terrain no human has ever seen. It captures terabytes of data. Pipelines, biology, geology. Nothing is hidden. For energy companies, it ensures infrastructure safety. For scientists, it reveals climate history.
They inspect thousands of miles of pipeline, checking for leaks.
Every dive brings back something new. A new species. A new wreck.
They aren't fast, usually 3 to 4 knots, but they never get tired.
They are nearly silent, disturbing nothing in the acoustic environment.
Surface weather doesn't matter. Down deep, it is always calm.
Over 24 hours, the navigation drifts only a few meters. Incredible precision. Forward-looking sonar acts as a bumper, preventing crashes into canyon walls. New designs mimic sharks and rays for better efficiency.
The next generation will stay down for months, charging at underwater docking stations.
Back on the ship, supercomputers crunch the data into three-dimensional models.
Beyond science, navies use them for mine hunting and surveillance. They are the only way to map the underside of Antarctic ice shelves. For the builders, seeing it return safely is the best feeling in the world.
Recovered, data downloaded, ready to go again.
The client accepts the vehicle only after a successful sea trial.
From Norway to the USA, this is a global manufacturing race.
We have explored less than 20% of our oceans. These machines will change that.
These machines are the eyes of humanity in the deep. And we are just getting started. The ocean is waiting.